Alright, so let's go through some complex patterns of inheritance. I'm going to work these problems out with you, so I want you to make sure that you're working them out on your note guide. We are going to start with a review of Mendel's laws. When we did Punnett squares, you saw that there were 3 laws. Law of dominance, where some alleles are dominant, others are recessive. Law of segregation, organisms inherit 2 copies of each gene, one from each parent. So mom can only give one, dad can only give one. And then law of independent assortment that says that one trait separates independently from another trait. So things don't tend to go together. However, this is called complex patterns of inheritance, and we're going to look at the rebels of genetics, things that do not necessarily follow Mendel's laws. Alright, so chromosome theory of inheritance says that genes are located on chromosomes, and the behavior of chromosomes during meiosis accounts for inheritance patterns. There are some exceptions to Mendel's laws, which I said were the rebels. Some alleles are neither dominant nor recessive, and many traits are controlled by multiple alleles on multiple genes. The exceptions to these laws include incomplete dominance, multiple alleles, codominance, and polygenic traits. And we're going to go through each one of these. We'll start with incomplete dominance. Incomplete dominance states that the heterozygous phenotype is somewhere between 2 homozygous phenotypes. So in this situation, the red is like homozygous dominant, maybe big R, and the white is homozygous recessive, little r. Those cross, and we end with a big R, little r, pink flower. So when you think incomplete dominance, think red plus white equals pink. Neither allele is completely dominant or recessive. So let's practice one of these. Okay? So we have, in humans, curly hair is completely dominant to straight hair. The heterozygous individual has wavy hair. So I'm going to pay attention to all of my vocabulary, and I'm going to highlight the heterozygous individual has wavy hair. And then here it says cross 2 people with wavy hair. So we know that we are crossing big H, little h, times big H, little h. All right, when we cross these, we get big H, big H, big H, little h, big H, little h, and then little h, little h. So when we look at these, we see that we have the genotype ratio of 1 to 2 to 1, which means 25% homozygous dominant, 50% heterozygous, and 25% homozygous recessive. Now, if we were doing our phenotype on a normal Punnett square, we would have a 3 to 1 ratio. But in this situation, the phenotypic ratio stays exactly the same. In this case, we would have 25% would be curly hair, 50% would be wavy hair, which is the mix, and 25% would have straight hair. And remember, when you're doing these ratios, it's like an understood fraction. So it's like these are over 4. So 1/4 is 25%, 2/4 is 50%. All right? So now we have 25% curly, 50% wavy, 25% straight. Let's try another one. Fitz loves growing flowers for his friend Olivia. Her favorite flowers, roses, are found in red, blue, and purple. So here's where I can look to see my genotypes, and I'm always going to do that. What would happen if Fitz crossed a blue rose? So we know, if Fitz crossed a blue rose with a purple rose. All right, so in this situation, we have a blue rose, which is little r, crossed with a purple rose, which is heterozygous. And every time we think incomplete dominance, we're going to think mixing paint. So now we have big R times big R, and then little r times little r, which gives us a 1 to 1 ratio. Some of you said 2 to 2, but remember, everything's over 4. So if I'm 2 to 2 over 4, I can reduce that to 1 to 1. In this situation, my phenotype would be the same, so it's 1 to 1. So we have 50%, that would be purple, and 50%, that would be blue. Okay? All right. So let's move on to complete dominance. Codominance, not complete dominance. Codominance is when we cross two things and they don't mix, they're both shown, and they love to use horses and chickens for these, speckled chickens. That's when red plus white equals red and white, not a mix of red and white. We're not making pink. We're doing red plus white equals red and white. So let's look at the difference here between codominance and incomplete dominance.
I'm gonna make a cloud. Whoa, that was awesome. And today we're gonna be exploring weather.
Welcome to Moo Moo Math and Science. In this video, I'd like to talk about incomplete dominance and codominance. Gregor Mendel is the father of genetics. He is famous for his pea plants. He would cross pea plants and study the offsprings. The traits he studied had two alleles, and one would mask the other trait. However, life does not always act this way. Sometimes you get a mixing of traits, or both traits appear. In other words, a third phenotype. In this video, I'd like to talk about the difference between incomplete dominance and codominance. With incomplete dominance, when you cross two individuals with two different phenotypes, you get a third phenotype that is a blending. You end up with something that is in between. Think of mixing paints. If you mix red and white, you get an in-between color, which is pink. Blue and yellow is green, again in between. Here are some real-life examples. The snapdragon is a mix between a white and red flower, and you get an in-between color, which is pink, an example of incomplete dominance. This hen is the offspring of a white and black parent, and you get this in-between color, which is kind of gray and kind of blue. With codominance, both traits appear. Remember, co means together, like cooperate, which means working together. One common example involves a white and brown cow, and you get a spotted cow, which is both white and brown. A speckled chicken is an example of codominance. The black and white alleles cooperate, and both appear together. A fork-like plant is another example of both alleles appearing. They are cooperating and appearing together. So there we go, the difference between incomplete dominance, which is blending, and codominance, which is both of them cooperating and both appearing. Thanks for watching, and Moo Moo Math uploads a new math and science video every day. Please.
Okay, so let's practice one. This one is going to feel like a rule breaker because in Punnett Squared you've always been told not to mix letters. But in this situation, because of the problem here, gray horses are codominant to white horses. The heterozygous horse is an Appaloosa horse. Cross a white horse with an Appaloosa horse. All right, so if we cross these two, we're getting a white horse, which is WW, times an Appaloosa horse, which is GW. So now we're going to set up our Punnett square with a letter mixing. And don't panic because that's what these are supposed to look like. So we've got WW times GW. When we cross this, we get GW times GW. Then we have a white horse here and a white horse here. So if we cross this situation, we have a 1-to-1 ratio, which is 50%, 50%, and the phenotype would be the same. So half will be gray and white, half will be solid white, and that's because we started with a solid white horse. Don't forget that. All right. Now we're going to do something called multiple alleles, and it deals with blood type. This, of any of the problems that we do, I would dare say this is the most confusing. So make sure you pay close attention to the lovely Amoeba sisters as they explain blood types and multiple alleles.
There's a lot of phenotypes that are easy to tell. Your eye color, your hair texture, your height, whether you have a straight thumb or hitchhiker thumb. But one phenotype that you can't tell just by looking is your blood type. Your blood is really made up of many things: platelets, plasma, red blood cells. But you've probably heard before that when blood is donated, it's very important that it is matched correctly. And that's true because blood type phenotypes vary. It really boils down to the fact that red blood cells, they're not naked. They have proteins on their surface. And it turns out that your immune system is very protective, and if it gets blood that's donated that has different proteins that it's not used to, it will attack them. With blood type, you can have several different phenotypes: A, B, AB, or O. These letters stand for antigens that are found on the red blood cells. So type A blood, for example, has A antigens on the surface of red blood cells. Type B blood, for example, has B antigens on the surface of red blood cells. Type AB has both A and B antigens on the surface of red blood cells. Type O, I like to think of it looking like a 0. It doesn't have A or B antigens. It's naked. Well, okay, it does have other proteins on its surface, but not A or B. So think of O as looking like a 0. Doesn't have A or B. So if you have type B blood, you have B antigens on the surface of red blood cells. That means a person with type B can accept another person's type B blood because B is an antigen that their body recognizes. But if you try to give that person a type A blood type, that's an antigen that the immune system does not recognize. That person's immune system would attack. It would also attack AB blood because that includes the A that it doesn't recognize. Now type O would be safe. Remember, O, think of like a 0. It doesn't have A or B antigens, so type O can donate to everyone. Now, while O individuals can donate to everyone, they can only receive blood from another type O. Because type O doesn't have A or B antigens, so their immune system will attack any other blood type that does. Neither of us have type AB blood, but we would think this is a cool blood type to have in the sense that you could receive blood from anyone. If an AB person received blood from a person that had type A, well, they've got the A, so it's all good. And if an AB person received blood from a person that had type B, well, they've got the B antigen too, so it's all good. They can receive blood from type O too because there's not any antigens to even worry about. Now, one thing we do want to add that makes all of this a bit more complicated: blood types also have a plus or minus sign listed by the blood type. This makes a big difference with blood donations. If you have a plus, it means that you have this other little protein called Rh factor on the surface of your blood cells. And if you have a negative, it means that you do not have this little protein called Rh factor on the surface of your red blood cells. Now, we're not going to be able to go into that in this short clip, so to the Google for that if you would like to learn more about this. Blood type is genetically inherited, and a great example of multiple alleles. Remember that alleles are a form of a gene, like a flavor. Just an analogy. So let's put this into practice. Let's say a couple gives birth to a baby boy. Both parents have type A blood, but then there is a mix-up at the hospital. And now, sorry, I get really into my drama. There are these two baby boys, and the hospital does not know which one belongs to the couple. Probably not a hospital where you'd want to have kids, but let's try and use our blood type genetic problem-solving skills to help us out here. Baby Phil has type B blood, and baby Sylvester has type O blood. Could either of these babies belong to the couple who both have type A blood? Well, let's talk about phenotypes and genotypes. The phenotype of type A blood is A, but the genotype is written like this or this. The format of writing here helps with multiple alleles like blood type problems, and we can show you why when we work this out in the Punnett square. Now, you may notice that I said that blood type A could be written this way or this way. Without testing, we don't really know which one it is. You can consider this one to be homozygous and this one to be heterozygous. The phenotype of type B blood is B, but the genotype is written as this or this. The phenotype of type AB blood is AB, and the genotype is written this way. There's no other way to write that one. The phenotype for type O blood is O, and the genotype is written like this. Remember how I said that the O kind of looks like a 0, and so you can think of it as having 0 blood type antigens? Well, that's what it is. Little I, no coefficient. Okay, back to the babies. We are told the parents both have type A, but remember, we don't know whether that means they are this type A, the homozygous, or this type A, the heterozygous. And the mom could be one of those genotypes, and the father could be the other genotype, or they could both be the same genotype. We just don't know. Okay, so let's try it out with all of the possibilities. Remember that we write the parent genotypes on the top and the side of the Punnett squares, like this. We'll fill in the Punnett squares, and we'll make sure to have capital I's first, just for formatting purposes. Okay, so is it possible to get baby Phil, who has type B, in any of these offspring? Nope, he must be someone else's baby. What about baby Sylvester with his type O? Yes, it is possible, but both parents would have to be heterozygous A. That means they both must be this. Then yes, you would have a 25% chance, that's 1 in 4 here, of having a baby with type O blood. Of course, if I was advising this couple, I would also insist on a DNA test, as this blood type problem only shows that it's possible that baby Sylvester is theirs. Well, that's it for the Amoeba Sisters, and we remind you to stay curious.
All right. So we realize that there are multiple alleles, multiple versions. I recommend this chart that's at the bottom right corner of your screen. I recommend you write that down because that's going to help you when you're doing these problems. Okay. So if a mother has type AB blood, so we are going to put I because I represents blood, and we're going to put IA and IB because since she has type AB, we know that she has one allele for A and one for B. Crosses with a father with type B. Here's what we don't know. We don't know if he is homozygous B or if he is heterozygous B. So we have to set up both. We know that she has to be this because only one letter is on each I. So now we cross it. Okay. In that situation, you just leave it blank because there's no antigen present. And then it would be, I'll move that out of our way real quick. So all the possibilities are, we can have AB blood, here, here, here. We can have B type blood. So we see that here, and here, and here, and here. And we can have A type blood because we see that here. So we can get these 3 types of blood from crossing those parents. Remember that I equals blood. And it actually equals blood with no antigen. Now, if we wanted to be more detailed, we could say that we actually have 2 types of this because we have the heterozygous and the homozygous types. Okay, so there's lots of different alleles for blood. Lots of different situations and scenarios. And these can be kind of tricky, so just take your time with them. Alright, the hospital has made a big mistake and lost track of which baby belongs to each parent. Can you help them fix this before they get sued? Alright, so we have babies that have, baby 1 has O blood, baby 2 has AB blood, and baby 3 has A blood. So baby 1 we know has to have this. Baby 2 has to have this. Baby 3 could be this or this. And we're not sure which one. So we're going to try it out. First we have these parrots. See if I can get that to go away. Can't get that to shrink down. Alright, so we have these parrots. We have Mr. and Miss Allele, and they are A, B. Ooh, I'm forgetting my I's. Oh my goodness. So we have IA times IB, IA times IB. So we've got these possible blood types there. Now we have Mr. and Mrs. DNA, which are I times IA, IB. That's the only option they could be. So we cross those. Okay. Now we have two Punnett squares for the last two because we don't know if this B right here is homozygous or heterozygous. So we know that the I's are going to be the same for this O parent. But on the B, we're going to have to cross this and then this. Okay, so let's cross it. We have IBI, IBI, IBI. And then we have an II here. So we have an O type blood here. Okay, now we have an IBI here, IBI here. We have an O and we have an O. All right, so are there, besides, let's look, baby 1 is O type blood. Who must be baby O's parents? Okay, there's only one situation where we have O type blood, and that's Mr. and Miss Jean. So, Mr. and Miss Jean have to be baby 1. Because that's the only one that has the O type blood. Alright, who has AB blood? Right. So we only have that situation here. So that was crossing Mr. and Miss Allele. Has to have baby 2. And then which one has baby baby 3? That would be Mr. and Miss DNA, because here's your A type blood here. So Mr. and Miss DNA would equal 3. Alright, so you can see how this might be utilized. And like I said, even looking at my screen looks a little tricky. So take your time on those blood types. They can be a little tough. We'll practice them a lot. Alright, multiple alleles, once again, is like blood, having more than 2 alleles for one gene. Examples of this are blood type, fur color in rabbits, different things. But the only time we're going to look at multiple alleles is when we're looking at blood type. Finally, linked genes are genes that are like physically located together on the chromosome, so they tend to be inherited together. So people with blonde hair tend to have blue eyes. People with red hair tend to have freckles. That's because you look at this blue and the red, they're located close together, so they tend to move together. They have a difficult time being broken apart during crossing over. Sex-linked traits. This is the last one that we'll actually work out today. Males and females have exactly the same chromosomes for pairs 1 through 22, and those are called autosomes. The last pair, which is X and Y, are sex chromosomes. Females have XX, males have XY, and you can see those differentiated here on the screen. When you are doing Punnett squares that are X-linked, you have to use sex-linked, you have to use those sex chromosomes in the problem. So, you have the Y chromosome, which carries very, very, very few genes, but the X chromosome contains many, 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 many traits. Sex-linked genes are genes that are on either one of the sex chromosomes, X or Y, and for our biology class, we will not look at any Y chromosome genes. We're only going to look at the X ones. All right, genes on the X chromosome are X-linked. Females inherit gene as normal and principle of dominance applies. Males inherit the gene on the X, but not the Y. So that is why a lot of times if there's an X-linked disorder, males tend to get it because females have two X's. So the dominant X can hide the recessive X, where in males, they only have one X. So if they get the gene, they're going to display the trait. This is where the word carrier comes in. Right, I think on my next slide I have a video. I do. So we're going to watch this video really quick about sex-linked traits.
Would you like to know one of the most underappreciated pieces of cytoplasm out there? Platelets. We take for granted the function of our platelets, which are fragments of cytoplasm that help stop us from bleeding. They help our blood clot when we get hurt. But there is a disorder called hemophilia that can affect those platelets because special clotting factor proteins that are needed to work with the platelets may not work correctly. So even a basic cut could be dangerous for people with hemophilia because they could bleed continuously. We have many treatments for the symptoms of hemophilia, and this has greatly improved outcomes with this disorder, although it wasn't always that way. Hemophilia is a sex-linked recessive trait, which means it's different from the basic Mendelian genetic problems. What do I mean by that? Well, we still use the terms dominant and recessive for alleles, but this time, because it's sex-linked, the alleles are on sex chromosomes. This is the case with sex-linked traits. So what is a sex chromosome? Well, recall that humans have 46 chromosomes. Chromosomes are made up of DNA and protein, and they contain your genes. Well, 2 of your 46 chromosomes, they are called the sex chromosomes. In a karyotype, it is usually the last 2 chromosomes that are the sex chromosomes. The sex chromosomes are called X and Y chromosomes, but it has nothing to do with the shape of the chromosome. That's always kind of confusing, but please don't think that Y chromosomes are shaped like a Y and X chromosomes are shaped like an X. This used to always confuse me. It has nothing to do with their name. The reason they got their name is actually kind of interesting, so to the Google for that. Everyone has an X chromosome, but if you have another X chromosome, meaning you have 2 X chromosomes, you are female. And if you have a Y chromosome, meaning you have an X and a Y chromosome, you are male. There are also genetic disorders where you can have extra copies of sex chromosomes, but we will not go into that in this clip. Sex-linked traits are traits that are specifically on the sex chromosomes. Most sex-linked traits tend to be on the X chromosome because it is larger than the Y chromosome and it contains more genes in the Y chromosome. The disorder hemophilia is like this. Now we will use the letter capital H to represent an allele for having normal blood clotting function, and a letter lowercase h to represent an allele for having hemophilia. Hemophilia is a sex-linked recessive disorder, which is why it's being represented by a lowercase letter h. Only it must be placed on the sex chromosome as a superscript, like an exponent. A woman that does not have hemophilia could have the genotype X big H, X big H, or X big H, X little h. Because as long as she's got at least one dominant allele, that dominating allele will be what shows. So no hemophilia, since again, hemophilia is a recessive sex-linked disorder. The only way for her to have hemophilia would be the genotype X little h, X little h, because only when there is no dominant present will that recessive show up, at least in this type of trait. Now for a male to not have hemophilia, his genotype would have to be X big H, Y. Notice how I did not put anything on the Y chromosome. Again, most sex-linked traits are on the X chromosome. If he has the genotype X little h, Y, then he has hemophilia. He doesn't have 2 X chromosomes, so he cannot be a carrier. So let's say that 2 people that do not have hemophilia have children. However, let's say that the woman is a carrier. That means she is heterozygous. how do you do a sex-linked Punnett square cross for this kind of trait? Step 1. Identify the genotypes of the parents. So the mother was a carrier. She is X big H, X little h. She does not have hemophilia because of that dominant allele present, but she is a carrier. The male, if he does not have hemophilia, well, he must be X big H Y. There is no other option for him. Step 2. Place one parent on the top, outside of the square like this, and place the other parent on the left, outside of the square like this. Step 3. Cross them. For formatting purposes, place X chromosomes before Y, and you also write any sex chromosomes with dominant letters first. The results you get in the squares would be the offspring, the babies. The genotype ratio could be written out like this. The phenotype ratio, remember that these are the observable traits, can be written out that there is a 75% chance that the child will be born without hemophilia and a 25% chance that the child would have hemophilia for this boy here. You could also make this a ratio, so 3 to 1. Notice that in this type of example of a sex-linked recessive disorder, males are more likely to inherit this disorder because there is only one X chromosome present. This is true for many other sex-linked recessive disorders, such as color blindness. Well, that's it for the Amoeba Sisters, and remind you to...
So let's practice. Color blindness is also sex-linked. Hemophilia is really cool to look up. It's known as the royal disease, and I'm going to put that as a discussion board. I want you guys to tell me why it's known as the royal disease. But now let's look at this problem. So color blindness is a sex-linked recessive trait. So normal vision is X with the big B. Color blindness is X with the little b. Y does not carry the gene. So we are going to cross a woman who is a carrier. Carrier means she carries the trait, but she doesn't have it, with a man who is normal. And I kind of hate using the word normal, so we're going to say a man who does not have color blindness. All right, so we're going to cross the woman who's the carrier, so that means she has a big B and a little b. This is the one right here that is the gene for color blindness. She can pass it on, but she is actually not colorblind, with a man who is not colorblind. Okay, so we'll cross that. So in this situation, neither parent is colorblind. They may not even know they carry the trait, probably do not know that they carry the gene for color blindness. So we're going to cross this. We have to keep the sex chromosomes in our offspring. And the reason is this situation right here. We need to know that this is a carrier. So she has a 25% chance of having a girl that is a carrier. And then she has a girl that is neither colorblind or a carrier. Now we're going to look at the boy situation. We have a 25% chance of having a boy that is not colorblind, but we have a 25% chance of having a boy that is colorblind. These are affected. So this one here is a carrier. It's female because it's XX. And then here, this is a male with color blindness. Okay. You can see why males tend to be affected more by X-linked traits, because they don't have another X to cover up or to hide that recessive allele. All right. That is it. So I'm going to stop here, and we will go over these at our next Google Meet.